Right. Hello, everyone. My name is Yu, and today I'm going to tell you about non-convex matrix completion. This is a joint work with Rong Ge from Duke University. So matrix completion is the following problem, where there's a hidden low-rank matrix, and you get to observe a subset of its entries, say uniformly at random, and the goal is to recover M star from these observations. So a signature application of this problem is in recommendation systems, where some user rated some movies. And the reason you believe this matrix is low rank is, say, you think every movie can be summarized by some features, and the number of features should be much smaller than the total number of movies. And you want to predict other entries because you want to sell movies to people. So this problem traditionally are solved using two types of approaches. One is the convex relaxation, where you minimize the nuclear norm of your matrix, subject to it agrees with everything you observed. It's a relaxation because you really want to minimize the L0 norm of the singular values, but you minimize the L1 norm instead. But magically it works. In this talk, I'll focus more on the non-convex approach, which is very natural, that you just minimize the sum of the square loss on all the observed entries. So ideally, you want Frobenius norm, but if you don't observe an entry, there's nothing you can do. Okay, so this problem's been studied extensively, and we know these approaches pretty well. When the entries are observed uniformly at random. So we know how large P needs to be for exact recovery, why gradient descent works, and when they work, with or without initialization. So the motivating question for this work is, what if instead of observing them uniformly at random, you get to see more entries? Okay? So intuitively, this only helps you because you get more information. So we want to ask, do the existing non-convex algorithm work? And if, spoiler alert, if not, can you fix them? So basically, we answer these two questions. So the answer is no and yes. It's a summary of our results. So we show you that no, they do not work. And we give you a very efficient pre-processing step, such that after this step, you can run gradient descent. Let me start with the counterexamples. So this is not going to be an exact counterexample, but I hope it conveys the intuition. So the underlying matrix is just the all-ones matrix. It's a rank 1. And we observe way more entries on the diagonal block compared to the off-diagonal block. This is the semi-random setting. And the local optima you are stuck at is this one, where you get all your diagonal block entries correct, and the off-diagonal blocks horribly wrong. So why this is a local optima? Let's say you want to move from the current point, 1 minus 1, to the ground truth, okay? And let's consider what happens when you just move a little bit to this vector here. So if you multiply it out, you will get this matrix. So for this matrix, you are doing better on the off-diagonal, and you're doing worse on this diagonal block, okay? But because you observe way more entry in this diagonal block, this actually make the objective function worse. So intuitively, you're kind of locked in by your diagonal block. Okay? This is bad. Okay, good. So how can we fix that? So let's pause and think for a bit, what went wrong in this counterexample. Okay. So if I knew the adversary is changing the probability in this way, then I can basically undo his influence in the following way. I can just assign a smaller weights to the entries in the diagonal block, or I can do some subsampling on the diagonal block to basically get my uniformly random matrix back, right? Then by previous work, I know that gradient descent works. So the key idea for this part is I'm going to try to reweight the samples so the input is similar to a random input. I'll define what similar means formally later. So just for a sanity check, this is not hopeless because a good set of weights exists. If I can just assign 1 for the entries revealed by nature and 0 for the entry added by the adversary. Okay. Right. So let's convert this matrix weight problem to a graph problem. So what I do is I will draw a bipartite graph between the columns of the matrix, rows and columns of the matrix. And this is the graph that I get from the input. Okay. So what is this input? This input is basically a random bipartite graph, or Gaussian random bipartite graph, plus some additional edges. Okay. What do I want to achieve on this graph? What I really want is, say, I want to recover this graph revealed by nature, right? Because if I can do that, then because it's a random graph, then I can run gradient descent. Okay. So suppose to pause here and ask you what went wrong for this. So this is impossible because the adversary can just reveal you another Erdős random graph. There's no way you can distinguish between them. So it turns out that as long as you recover a graph that is spectrally similar to a random graph, then or spectrally similar to the complete graph, then that's enough. Okay. So one of the main technical contribution of this work is we show that how you can solve this problem in nearly linear time, if epsilon is constant. We can solve this for any underlying graph, not just the complete bipartite graph. And the way we solve it is to adapt techniques from the spectral graph theory. It's not an immediate implication, but you can just open this algorithm and change a few things, and it will work. Okay. So so after you obtained this weights from your pre-processing algorithm, you can convert them back to the matrix thing. And the other technical contribution of our work is to show that spectral similarity is sufficient for you to eliminate all the bad local optima. Okay. So basically, these 2 arrows are like what happened to 90% of the writing of the paper. Okay, good. So besides these technical contributions, I'd like to end with the what I think is the main conceptual contribution of this work. So we're in this setting where you have a non-convex algorithm that's efficient in practice, but it doesn't work in our semi-random model. So what we did was before running this, we used a lightweight convex optimization algorithm, which we borrow from spectral graph theory. And then you kind of get this combination of 2 things, that you get to enjoy the efficiency of non-convex algorithm, but they are also robust to this semi-random adversary. Okay? And that's it. Thanks for your attention.
Any questions for you? All right. Looks like there'll be good poster discussion. Everybody's contemplating things. Okay, so the next